Welcome to the last video in our video series on the new 2023 National Building Code Alberta edition. The new code is out and we've been using it for a while, but we just wanted to talk to you about the topic of peak cooling loads. My name is Daryl Paul and I'm a building envelope specialist and an energy advisor. And I've been working with things like peak cooling loads, energy efficiency for a number of years. What we're going to discuss in this video is dealing specifically with peak cooling loads. What are they, why they're important, and what does the building code have to say about them? With the peak cooling load, what we need to understand is why we have to calculate this peak cooling load. Now, one of the issues is when we get into summertime, we have an extreme amount of heat sometimes, depending on the climate. So if you're in an area where you get a lot of sun coming into the building, and depending on your windows, depending on the direction they face, you could overheat that house quite quickly. And what we know from peak cooling loads is the fact that when you overheat the house, the amount of energy in there makes it very difficult for your body to cool down enough. So it becomes a health and safety issue. And so that's where the new code talks about peak cooling loads and how to calculate those so we don't put the occupants in danger. Now, why would that be an issue? Well, in Alberta, we don't get significant amounts of humidity, but we do get significant amounts of heat. But what about in a climate where we get quite a bit of heat and humidity? Well, there's where the danger comes in. In the study that was done by NRC, they found that over the course of the last 20 years, from 2000 to 2022, there was over 670 deaths as a result of excessive heat in buildings. And a lot of that has to do with people who are housebound, who can't get out of the house, people who are elderly. And when that happens, they have no way of cooling down, especially if that heat is combined with high humidity. So that's where the building code came in and said, we need to make this change to incorporate the peak cooling load, the maximum amount of heat that can be built up in a house, so that we don't cause harm to the occupants. So if you recall in our earlier videos, we talked about tier codes. Now, Alberta didn't adopt the tier code in the sense that in 936.7 and 936.8, that's tier codes for performance and tier code for prescriptive. Those were not adopted. So we don't have to follow the tier portion, which in the performance aspect is where peak cooling loads are listed. But what we can do is if we voluntarily choose to follow that code, in other words, let's say we decide we want to voluntarily follow the tier 3 portion of the code, now the peak cooling loads will become a requirement. So there's a caution there in terms of what you want to take on and what you don't. So we'll talk about what the peak cooling load does, and it really depends on the type of building that you're constructing. Because if your building is a single family house and you have lots of windows on all 4 sides and you have the ability to turn that house, then it probably won't affect you too much. If you're building a multifamily where you're limited in one side facing south or west and you have lots of glass in there, you may be going to have a difficult time with the peak cooling loads in that situation. So if we voluntarily choose to follow that path, peak cooling loads become part of your code compliance. Now, what does the code actually say? Well, if we look at 936.7, which is the performance aspect of the tiered energy compliance path, let me read what it says. In sentence 2, it says, the peak cooling load for the proposed house shall not be greater than the peak cooling load for the reference house. So number 1, we have to do an energy model, and typically we'll use HOT 2000. We do an energy model of the proposed house, remember. So we put all of the data in, the geometry and what insulation values, solar heat gains on windows, all those things. And it tells us what the peak cooling load will be for that proposed house. Then we create the reference house, and the reference house also will give us the peak cooling load. Remember, that reference house, the windows, the solar heat gain is based on 0.26 solar heat gain. So there's not a lot of heat coming through the glass in the reference house. So when we compare the two buildings, we have to have an equal or lower value in our proposed house to be compliant with the current code. So that's the first thing to remember. The second thing it mentions here is even if no cooling system is installed, the models with appropriate size space cooling equipment are used for calculation. So we would include the air conditioning in that calculation, and whether we include it or not in the HOT 2000 model doesn't make any difference in the calculation of the peak cooling load. The peak cooling load is the amount of internal gains, so from people, how much heat you give off, from the lighting in the building, all the appliances, plus the amount of solar gain from the outside or the temperature outside, or even the air leakage coming into the building. The total amount of energy from all of that is what we calculate the peak cooling load to be. Now, what's the purpose of the peak cooling load? Well, it's a way to calculate our air conditioning when it comes to our mechanical systems. But when it comes to health and safety, let me tell you what the real definition is. It says that the peak cooling load is the maximum rate of heat removal required to maintain a building or a house at a cooling set point temperature under the most extreme conditions over the year. So if you build this house that we're in Calgary, you're going to have a different peak cooling load than you will in Edmonton, or in Lethbridge, or in Fort McMurray, because we're in a different climate zone. We have different amount of light coming in from the sun. We have different directions that it could be facing. That could influence it as well. So it's pretty specific to where you're building and the direction it's facing. And that's where the challenge comes in when we're building and we have to accommodate peak cooling loads, because a single family house is going to be totally different than a multi-family constructed building. So how would you do a peak cooling load calculation? Well, just like the name says, it's what's the peak amount of cooling that's needed. It's the complete extreme opposite to what the heating calculation is when you're looking at a heat loss calculation. So in the wintertime, because we're in cold climate, we always think about the heating. And when you think of the heating, you think of, okay, we need more insulation in the walls and we need better windows. And the reason being is we want to keep the heat in. Well, the peak cooling load is the exact opposite. We want to keep the heat out, and we want to be able to keep the occupants inside warm in the wintertime, but we want to keep them cool in the summertime. Now, the challenge is if you have a lot of humidity in the house, the humidity is what causes part of the problem. In fact, it causes a big part of the problem, because when you're sitting in a house and you're trying to get rid of that heat, your body naturally perspires. And if it's perspiring and the air is dry, then you have what's called evaporative cooling, and you feel cooler. But when the humidity is really high, your body can't get rid of that moisture, and you don't get that evaporative cooling. So that means that the heat builds and builds and builds. So if you're in central BC, you're in Toronto, you're in somewhere where it gets not only hot, but really humid, it makes it very difficult for your body to get rid of that heat. And that becomes a health and safety issue. So when we calculate this, we look at the climate we're in, we look at the amount of sun we get, and that's all done within the software. But what we need to do to establish that is we need to look at what the insulation values are. Well, we've already done that for the heat loss calculation. We look at the windows. Well, we've already done that for the heat loss calculation. We look at all the internal gains. Well, the software pops those in there. But one thing that we can look at specifically is what's the percentage of glass in the house, but specifically to the direction that gets sun. So your glass, if you have a large percentage in the direction of the sun, that's going to let a lot of heat in. And you may recall we talked about solar heat gain coefficient, or the SHGC. That is what dictates how much heat from the sun comes through the glass. So if you have a solar heat gain coefficient of 0.7, you're going to cook yourself, because there's so much heat coming through there in the summertime. Nice thing about it though is in the wintertime, it's going to keep you nice and warm, and it's going to reduce your heating costs. So ideally, if you put a high solar heat gain in, and then you put some shading on the outside of the building, that shading would block the sun in the summertime, and you would get really good benefits from that. But can you imagine trying to build and construct a modern house and having to put shading over every window? Now you can design the overhangs so they block the sun when it's higher in the sky in the summertime, but again, there's a lot of calculation involved, And with smaller overhangs and modern designs, it doesn't really lend itself to be able to accommodate that. So the easiest way to do it is to choose a window that when you calculate the overall heat gain from the glass, you get the right solar heat gain calculation. Now, when we're doing that calculation, you would put the solar heat gain and the U value of the window into the software. And when you're done, you would get a report. For instance, if you're using HOT 2000, you would get a report and you would scan down to the bottom of the report and there would be a design heat load and a design cooling load. And you're looking at the cooling load. It's either going to be BTUs per hour per square feet, or if you're using metric, it's going to be watts per meter square. So let's assume we're using metric, it's watts per meter squared. When you get that number, then you take the reference house, you look at the housing report or the full report, and you scan down and you see at the bottom of that one, and you see where that number is. And you need to be equal or less than. Now, if you find that you're a little bit higher, then all you have to do is go back to your windows and reduce the solar heat gain. So let's say you're using a 0.4 for your solar heat gain, which is kind of mid to lower solar heat gain. You find that you're a little bit too high. Well, now you go back and you change those to 0.35 solar heat gain, and then you redo the calculation. Now that'll bring it down a little bit. Is it enough? Maybe, maybe not. Then you do another calculation and you bring it a little bit lower until you reach that point where you are comfortable that your peak cooling load isn't exceeding that number. Now, when you're doing these calculations, remember, this should be done way before you choose to do the construction. If you choose to do this calculation right at the point where you're applying for your building permit, you probably have already ordered your windows. So if your solar heat gain is too high, that's going to create a problem. And just because we haven't adopted it currently in our current code doesn't mean that that won't change. So we have the current code for the next few years, but if the government changes or policies change, and if they choose to introduce the tier codes, now we could have that peak cooling load introduced. And we know from the next edition of the code, there are some changes which both help and hurt us when it comes to the energy efficiency, but they will make improvements in what the peak cooling load is telling us we have to do. Now, as far as the calculations go, that's the simplest way to do that is when we're talking about single-family dwellings. When it comes to multifamily dwellings, now we also have the situation where if we're doing townhouses in rows, we end up with two sides of the building, and if one side has a lot of glass and faces that sun side, which is south or west, then we can get excessive heat buildup as well. So we need to think about the positioning of those buildings. And then thirdly, when we get into townhouses which only have one face that's exposed, now we have a large percentage of glass to wall ratio. So remember, there's the FDWR, or fenestration to wall door ratio. And if we keep that low enough, we don't have as much problem either. So think back to the FDWR calculations. If you looked at your energy model, you would see that you would have a number probably somewhere in the 8 to 10% range. That's an average. If you have a house that's got, say, 40%, and you have a very high percentage of glass, your risk of having a peak cooling load that exceeds what the reference house is goes way, way up. So you need to think about the amount of glass, you need to think about the percentage of glass in that face. And remember, when we're calculating for multifamily, we're calculating the exterior wall faces. So if you only have one face and you have, say, 16 feet wide by 3 floors, the amount of glass that's in there is going to be higher. In a lot of cases, you're up into the 25-30% glass to wall FDWR, which creates all sorts of challenges currently with the way the code is currently written. Now, thankfully, there are some changes coming which will offset that, but let's go through a couple of calculations and see what the real world impact is when you do the energy modeling. So when it comes to peak cooling loads, there is a calculation we can do. So I'll walk you through this because in my mind, I want to know what the real world numbers would be. But before we talk about that, we talked about solar heat gain and the fact that that is what lets a lot of the heat come through. But we just touched on shading. So let's talk a little bit more about shading first. If I put a shading on the outside that blocks the sun during the most intense period of sunlight, that can have the same impact as going with a low solar heat gain. But if I can remove the shading in the wintertime, remember we said that we could increase the free heat that the sun gives us. So that's an option. However, when we're talking about shading, don't think that we can use blinds or curtains on the inside. The challenge becomes, and the issue becomes, is if you have an intense amount of heat coming through the glass and you choose to put something inside, the risk is you can overheat that glazing. And so depending on where the layers of film are, the low E coatings, which is the low emissivity, which reflects the heat back and helps us to reduce the solar heat gain, and depending on how many layers of glazing we have. So for instance, with 2 layers of glazing, we have 4 faces of glass that we can reflect the sun and the heat back. When we have a triple glazed window, we have 3 layers of glass, which is 6 faces. But if we're reflecting that heat back and forth and we choose to put something on the inside, which will help in the room to reduce the solar heat gain and the heat generation, but in doing that, we could generate a significant amount of heat between the glass and that curtain or that shading on the inside. So we really don't want to do that. That can create all sorts of problems for us. So let's talk about the calculation. One of the simplest tools we use is HOT 2000. Now that's something most energy auditors, energy modelers will use to do their calculations. It allows us to meet the code compliance. It allows us to do EnerGuide, Energy Star, and other rating systems. Now, when we put the information in, we get a report back from the software, which gives us some information. So I did 2 different models here. So I did a model on a single family house. And what it showed us was on about a 2,500 square foot house, when I go to the peak cooling load, when I hit the highest percentage of glass facing into the sun, my peak cooling load in the proposed house is 6,400 watts per meter square. So that's the amount of heat that would be generated in a house. If I take that house and I turn it optimally so that most of the glass is in the shady side, then that drops it down to 4,300 watts. So it's a significant difference in the direction that house is facing. That's all with solar heat gain glass that's 0.4 of a solar heat gain value. Now, the overall percentage of windows in this house is 13.8%, so not excessive, but you can see the impact it has when I turn the building. Now, if I take that same house and all I do is take it and put it where it's facing straight into the sun and I got 6,400 watts of heat generation in the design peak cooling load, then when I reduce that to 0.24, I pull that down to 4,300 watts. And that's what the reference house is. So for this particular house, if it's facing a direction that's getting the most of the sunlight through the windows, I can't use a 0.4 solar heat gain glass. I have to drop it to 0.24. Question is, can I get a 0.24 solar heat gain glass in a triple glazing? So that becomes the challenge. So that's a single family house. Let's try it on a multifamily house with only one face. This is where the challenge really comes in. So let's say I'm building a multifamily and I'm facing directly into the sun. So it's south facing. This particular house, because there's only one face, has 27% FDWR, or glass ratio to wall ratio. So at 27%, it generates 2,739 watts. That's the heat generation. So that's the design peak cooling load. The reference house is only 1,800 watts. So I'm almost 1.5 times, 1 3/4 times the amount of heat that I'm allowed to be. Now, if I turn that building, the problem goes away. As long as I'm not facing south or west, the problem goes away. But that's pretty hard to do in a multifamily site. So if I take those windows and I want to make the solar heat gain low enough, I would have to reduce the windows down to a 0.21 solar heat gain. I don't think they make a 0.21 solar heat gain in a triple glazed window. So there's where that doesn't work. We can't make that work. So I either got to reduce the amount of windows or I have to find a window that currently isn't even in production. So there's where the challenge is. So when it comes to the calculations, you would just simply pull a house report from the proposed, a house report from the reference, compare the two, and as long as you're equal to or lower than the reference house, then you're good and you're in compliance. So as we saw in the calculations, it makes it very difficult building certain types of structures to be in compliance with the peak cooling loads. One of the reasons why they're not being enforced right now, because it's very challenging, other than single family, to be able to meet those requirements. Now, when we think of different building styles, we think of different archetypes, you know, a 2-story versus a bungalow. If you were building a bungalow, for instance, and you had a 2-foot overhang, in a lot of cases, if you keep the windows upwards, in other words, you don't extend them down and make them 5 or 6 feet deep, keep them upwards, you have enough shading from the sun in the summertime that you can actually make that work pretty well on just about any direction. But in terms of archetype, as soon as you get into, say, a 2-story or a 2-story with a loft, 2-story walkout with a loft, you're starting into these very tall buildings. And if that face is facing directly into the sun, that's where you start to get into problems, because you're getting the full expanse of the sun on that full face of the building. And so that's heating up the building, it's heating up the glass, it's heating up the internal components within the house. And that's where the peak cooling load starts to get excessive. And that's the danger. So part of it is design, part of it is overhang size, part of it is the shape of the building. And some of those are dictated by the land, by the property, and some of them are dictated by the designer and the person doing the design of the building. So those are factors that we want to consider. We've already talked about shading and the benefit of using shading. There's things like awnings that could be used, power awnings that open and close. There's power shutters that open and close. So there's a number of factors that can be added to a building which will help you, and especially when you're moving into more high performance homes, when you're getting into net zero, where you really want to get that free heat from the sun in the wintertime, but you want to block it in the summertime. So as you look at this, you might kind of question, well, why does the performance path have the peak cooling load and the prescriptive path doesn't? It might seem a little bit unfair at first, but remember, we go back to when 9.36 was introduced, the energy code was introduced. And one of the easiest ways to meet that code was to put a high solar gain window into a house. And in performance modeling, we could really influence the overall performance model of the house simply by changing the solar heat gain of the window. That brings us back to a balance. Because we could get so much free heat from the sun in the wintertime, we could make our energy model perform really, really well. The problem was what happened in the summertime is we would overheat the house. And so the code was designed so that it would offset that and correct that. Unfortunately, there was a few things that weren't thought well enough in advance. So now we're looking to the 2025 version of the National Building Code to correct those issues. So as we mentioned in our opening comments, overheating can be a big issue, especially when we have high temperatures and high humidities mixed together. So there was studies done by NRC and by the Canadian Home Builders Association, and what they did was they determined how big of an issue this was. And then that went out for code review. It was introduced into the code. The biggest factor in all of this was the amount of deaths that the research indicated was happening. And as was mentioned, you know, this affects people who can't get out of the house. If you're in an apartment, if you're in a townhouse, you don't have enough opening windows. For instance, if there's only one side of your building that has an opening window, you don't get the wind or the air blowing through to bring in that cool. The other part of that is if it's high humidity, how do you get rid of that humidity? So a lot of times, we might rely on mechanical ventilation or mechanical systems to reduce the temperature. But what happens in the summertime when it's really hot is sometimes we can get these brownouts where the temperature is so high that everybody's running air conditioning and the electrical system can't keep up with it. Now in those situations, we can't rely on electrified mechanical systems to reduce the temperature. So we have to go back to the building code and look at the envelope, look at the windows, and look at the design and say, What's the maximum people can handle in the summertime when it's really hot and humid before they're going to run into problems? And so that's where the health and safety comes in. So it does matter. Now, it doesn't matter as much in a cooler climate, doesn't matter as much in a drier climate, but it does matter. So this national code has introduced this for us in this cycle. One of the challenges, though, is we've gone from one extreme, allowing lots of solar heat gain and free heat so that we can make our energy model perform good, to the other extreme where we're almost penalized for having peak cooling loads being too high. So there is upcoming changes to the building code. You don't have to worry about this going on and on and on. There is some adjustments being done in the 2025 version of the National Building Code. So the FDWR can be a little bit confusing at times, or we call it the fenestration window-door ratio, so FDWR. Now, the way we calculate that is we want to figure out the wall area, the heated space wall area. So we would take from the top of the ceiling of the wall, where the top of the wall meets the roof, and we would run that down to the base where the grade is, and then we would take the entire perimeter and multiply that. So that's the exposed surface that is going to be influenced by the heat change of the temperatures outside. And we calculate that, and we get the gross wall area. Now, we know the wall area. Now we have to figure out what the fenestration and door area are. Now, we want to do those separately because the door typically doesn't have glass in it. Now, sometimes you'll have a little piece of glass, sometimes you'll have side lights, but side lights will typically add in with the windows and calculate those together, because the difference between a door with no glass and a window is they both could have a U value of 1.2, but the window's also going to have the solar heat gain. And that coefficient is also going to determine how much heat comes in. So when we're calculating that, we need to know the door ratio and the window ratio. And then we take those out of the gross wall area, and now we have a net wall area, and we have a net window door area, and we divide that into the other one. So earlier we talked about a house that has 13.8% glass. Well, that's on all four sides. That's how much percentage of glass or fenestrations there are in relation to the wall area. So that's the FDWR calculation. So when you think of FDWR and building archetypes, or in other words, building styles, designs, stories, things like that, when we look at the two of them, it's really important to think about this calculation. So for instance, if you do a bungalow and you have four sides of that house to work with, and you only have 8-foot walls, your amount of windows and your amount of walls could be a lot higher than if you have a 2-story with the same amount of glass, but twice the amount of wall. So that affects the FDWR, which then affects the solar heat gain, the amount of sun coming through that glass. Now, you move from that of a single family home where it's relatively easy to move windows and spin things around, change from a bungalow, 2-story, up to a walkout. And then you go in and you look at, say, a zero lot line. A zero lot line, depending on the municipality you're building in, you may or may not be able to put windows between, whether they're fire rated or not. But typically, you're probably not going to have much glass between those units. But the actual wall area is going to count. So you might move the glass front and back, or you might just keep the same percentage. So on zero lot line houses, you might find that you're 5 to 6% in terms of the FDWR. That's a little bit different now when you move down the line and you say, let's do side-by-side townhouses. When we calculate the FDWR, we're looking at the exposed wall surfaces, and with a front back, you have a wall surface on the back, a wall surface on the front. So your FDWR now percentage goes up a little bit compared to a zero lot line because it's all exposed wall. Now, if you have a corner unit, you're going to have 3 sides. If you have a center unit, you're going to have 2 sides. So that means the FDWR goes up again. Then when you get into townhouses, which have 2 rows back to back, now you only have one face that's exposed. So now if you want to have enough light in there, the amount of glazing goes up, and so does your FDWR. So that means you're going to have a very difficult time meeting the peak cooling load requirement and being able to keep it at or below that reference house. So we've talked about the challenges of meeting peak cooling load requirements, especially for multifamily construction. For single family, we can typically adjust the solar heat gain and it really doesn't become a big problem. But when we get into those higher percentages of FDWR, now we've got a big challenge. So what's being done about it? Well, the 2025 National Building Code has put forward a change. The change is called PCF 1823. And what the proposed change is saying in the review documents is it's telling us that they're going to make some minor adjustments in how we calculate in the performance side, but we're also going to include a prescriptive calculation for those of us that want to do our compliance path for 9.36 Energy Code under the prescriptive modeling. And these involve the tier code 9367, 9368. So here's just a couple of things that are being proposed. And we don't know what the outcome is yet, but this is what the proposed change is going to indicate. So first of all, what they found was that a low solar heat gain of 0.4 or less is really where we want to be. That's the target number, is lower than that. So when we look at the FDWR calculation for performance, you remember that anything below 17%, we get a credit, which helps in our heat side, and anything above 22%, we get penalized because now it's going to be letting too much heat loss through. Well, the same thing applies to the cooling side of that. So anything between 17 and 22 doesn't have a big impact in terms of FDWR. Anything below 17 is going to help us, anything above 22 is going to hurt us. So what they're proposing is they're going to limit the solar heat gain below 17% glazing percentage to 0.45 solar heat gain. That's the prescriptive requirement. When you're at 17 to 22%, they're going to say it has to be at 0.4%. So how are we going to offset this? Well, the proposed changes mean that anything below 17% for a percentage of FDWR is going to have a solar heat gain of 0.45 or lower. Anything between 17% and 22% of the FDWR is going to be set at 0.4 solar heat gain. And then anything over the 22%, unfortunately, is going to have to go to the performance model. Now, what that means for high performance homes and large, big, fancy homes is that once you get into the 22% or higher, the calculation not only has to work for the heating climate, but it also has to work for the cooling climate. So that's going to have the biggest impact on custom home builders. Now, with the performance side, when we're doing performance modeling, remember our reference house is being calculated, the peak cooling load is calculated based on a 0.26 solar heat gain, and we put the windows in equally on 4 sides as our reference house, and that's our comparative for the peak cooling load. What that means is sometimes we get so close to being equal to or less than that we can't meet that. So they've actually, instead of being equal to, we can be 110%. In other words, we can be 10% over or under on that peak cooling load number, and it won't have the big impact. So that'll help us with most of our energy modeling to be able to accommodate that. But again, the biggest impact is going to be on those that build custom homes with lots of glass. It's going to make it very challenging in the next code cycle to be able to achieve what we could in this code cycle. So one thing to keep in mind is that these are proposed changes only at this point. They've gone out for public review. Everyone's had an opportunity who's reviewed this proposal to give their comments and make suggestions on what would be a method to improve the PCF or to adopt it or to choose not to adopt it in this code cycle. But chances are, because the current code penalizes parts of industry, that there will be some kind of change. So we'll just have to wait and see how that plays out. So what have we learned from our discussion today on peak cooling loads? Well, Some of the important factors are the amount of glazing, the percentage of FDWR on the wall, the direction that glazing is facing, whether we're doing single family or multifamily, and in multifamily, how many faces are exposed and which direction are those facing. We've also talked about how we do the calculation and what that calculation produces and how lowering the solar heat gain can give us a benefit when it comes to reducing the loading in terms of peak cooling load. A couple of the other benefits I found interesting is when we look at the overall impact. This was one of the studies, and it said that high solar heat gain windows offer energy savings of 13 to 17%. So that's that free heat from the sun. But if we compare that to conventional windows, a low solar heat gain window is 8 to 10% saving. So if we try and balance that, and we're in a heating climate where we also get a lot of sun in the summertime, our net benefit of having a 0.4, 0.45 window that meets and doesn't exceed that peak cooling load can actually still give us upwards of 10% improvement. So that's the importance of doing an energy model versus just following a prescriptive path. We can optimize the benefits that we achieve through the window calculations. So I hope you've enjoyed the information. I hope you've learned something. And remember, right now, this is not a requirement in the building code to enforce peak cooling loads unless you're voluntarily going to adopt one of those tiers. So in conclusion, unless you decide that you want to adopt one of these tier codes, you're not forced to follow the peak cooling load requirements. Although it is a good practice to try and reduce the overheating in a building, we still want to be careful, and that's where we can have a big impact when we do our design. When we do our energy modeling, when we do our performance modeling, we figure out what the peak cooling load, we get close to it if we can, but we're not forced by code to make those adjustments. So that'll help us to improve the energy efficiency, it'll help us to improve the comfort for our customers. So those are things to consider when we talk about peak cooling loads. So that concludes our video. We hope you've learned a little bit more about peak cooling loads. And don't forget to download your free copy of the 2023 National Building Code Alberta Edition. And by the way, if you don't like any of these codes, you can always get involved because that can have a big impact on future codes and an improvement in how we build houses. And of course, we want to thank a few specific individuals for their help in producing these videos. Rick Gratton from Brookfield Homes, Brian Prefontaine from Mattamy Homes, Cedar Glen Homes, Build Alberta, and of course the Safety Codes Council and PHBI.